Hello, class. Welcome back. This is the first of a series of videos I'll be creating for our next topic in the class, which will be functional programming in Scala. I hope you got my email in which I asked you to install the latest version of Scala compiler on your laptops. It's a pretty straightforward install. Just have to download the zip or the gz file and unwind it and then set the class path or set the path to execute the Scala compiler and interpreter. Okay. Anyway, if there's any questions on setting up the Scala system on your laptops, I can send a more detailed FAQ on how to do that. Okay. I also sent you another link called Scasti or Scasti. Here is the website, Scasti. You can actually log in with your GitHub account on the top corner there. And the advantage of logging in and creating an account would be to save some of the work you do here in Scala. It allows you to save and download, and I believe it also saves a copy of that in your GitHub account. But double check that. Okay. So this would be a workplace where you can try out small to medium-sized Scala programs. Okay. So either this online resource, the scasti.org or scalalang.org, and of course you can have Scala installed on your computer and run your programs there as well. Okay. All right. Today's lecture would get you started with basics. Okay. And as you can see here, I'm using Jupyter Labs. It's a with a Scala plugin. Okay, so very nice, convenient. Now, if you are interested, I can post FAQ on how to do this, how to get this installed as well. But let's see as we go along whether this is necessary. This is more of a useful teaching tool. It's more useful to the teacher rather than the student, these Jupyter Labs, at least the way I'm going to be using it. Okay. Anyway, so let's get started. Scala is a programming language, invented probably about 10, 12 years back. Odersky is the person who came up with this. It is built on top of Java, so there will be some familiarity with Java will help, but not very much in the sense that we are going to learn only the functional programming aspect in Scala. Okay? So we're not going to go into object-oriented and other aspects of Scala. So, but it does require a Java JDK underneath even the compiler which you install. Okay. In any case, let's get started. Okay. Before we actually get to functional programming in Scala, let's see whether let me increase the fonts a little bit more. Okay. And let me move this guy down there. Yep, so a little bit bigger. Okay, fonts. Hopefully, all of you can read this. Okay. Now I'm going to be posting these to the class website. These notebooks, both in HTML form and also the IPYNB format. If you're going to load up your own notebooks. Okay. So this is called a Python notebook or a Scala notebook, in which we can actually illustrate lessons like these. And as you go along, you can see that we can actually run code inside this environment as well. Okay. Anyway, get started. Let's look at where functional programming falls in the overall scheme of things. Programming paradigms are ways of styles of programming, and in general, there are three different types. Imperative programming is the traditional model which most of us learned, and that is you have a memory, you have registers inside your CPU, and you have a state. Remember, we talked about the state. We have variables, and then after you execute an instruction, the variables might change their values, okay, and so on. Okay, so that's the imperative programming, and you have control structures like if then else. There you go, loops. Oh, what happened here? Okay, so this is a feature of the Jupyter Notebook when I double click a particular cell. Now this whole thing is in a cell, and when I double click it, it actually goes to the edit mode, and that's why it showed something else. Okay. Anyway, there are if then else, loops, continue, return, etc., which are all inspired by the von Neumann architecture of computers. Right. All of us are familiar with imperative programming. Then we are going to learn functional programming. Some of it you probably already familiar a little bit, but these are this is a model in which programming happens without mutable variables. Mutable means values will change. Okay, so here we have variables possibly, but we want to code or write the programs without variables changing their values. Okay, and without assignment statements, without loops, without the control structures. I mean, we may have some limited if then else type of expressions, but not the traditional control structures. So a lot of the things you're used to in imperative programming are not available here. Okay, but we are going to heavily use functions, programming with functions, and the more important thing is that functions themselves become values. Right, so that's something you have to get used to in function programming. We got a flavor of that in the lambda calculus. Okay, and by the way, lambda calculus is a basis for all the function programming languages. Okay, so functions can be passed as parameters, the function values. Okay, the function values can be returned as return values of a function. Okay, so basically functions are also treated as values, just like numbers and booleans and so on. Okay, so very terrific programming paradigm, because it's very difficult to make mistakes if you write the code properly here. There's a third paradigm called the logic programming. I'm not sure if we have time to cover that in this class. I mean, last time I taught it, we did cover Prolog a little bit last 2 weeks. We'll say probably not, because of the 1 week we got off. Okay. Now these are the three paradigms which are parallel to each other, but there is another paradigm, object-oriented programming, which is orthogonal. Okay, so you could actually have functional programming within object-oriented programming, and that's really what Scala is. See? Scala is actually a language which supports lots of object-oriented paradigm or programming, but also has a very strong support for functional programming, as we understand, as is defined in the lambda calculus. All right. Okay, so let's get started. Functional programming in Scala. Okay. Now you'll see that I'm using the notebook. So when I go into this box here, this is called a cell. Okay, a notebook cell. Okay, and in this cell I can type. It's like the interpreter when you open up the Python interpreter, Python 3 when you're on the command line. Okay, or if you want, I can show you the Scala interpreter on the terminal for a moment. Okay, so here's a terminal, and I say Scala, enter. Okay, and I see the Scala interpreter, and then I can type the same expression, 87 plus 145, and hit enter, and it gives me the answer. Okay, so or you can write more complicated expressions on the terminal there. Okay, I'm going to switch. The same thing is happening inside the cell. So inside the cell, especially when the top part here, you see that there are 3 options there: code, markdown, and raw. If the option is code, and if I type something into this, that has to be valid Scala code. Okay, so in this case, 87 plus 145 is a valid Scala expression. Okay, and if I hit the run here, let me go back. Okay, there you go. Okay, so it took a while. Sometimes it's a little slow, but it gave me the answer below that. It says result 0. Now this is just a variable, internal variable, colon, and then it gives the data type of the output. Okay, in this case, the output is int. That's how you write int data type in Scala. Okay, you'll see some similarities with Java on the basic data types. Okay, because Scala is built on top of Java, the implementation. Okay, and then the value is 232 here. Okay, so that's a very basic expression, arithmetic expression in Scala. Okay, let's go a little bit more. Okay, here I'm defining a variable called size in the next cell and assigning it the value 2, and in front of it I put val. Okay, val, and then later on you'll see down here you can also say var. Okay, now you have to say val or var in front of it. Okay, there's a third option called def, def, and we'll see that, but usually on variables you put a val or a var. Okay, use val if it's a fixed value. Okay, later on I think there's a slide which explains the difference between val, var, and def. Okay, but anyway, val means it's a fixed value. You cannot change this variable. Okay, that's what it means. Okay, you can use it, but you cannot change the value of the variable. All right, so that just defines size equals 2. Okay, and if I want, I can run that cell. It's a little slow. Okay, when I run the cell, it takes that code and runs it and then prints whatever variable is defined there, in this case size int and 2. Okay, now the interpreter knows about size. Okay, so I can actually calculate another expression called phi times size and run it. Okay, and you can see that it pops up the answer int 10. Okay, so that's another that's how you do arithmetic in Scala. Okay, so that's very basic how to declare a variable which does not change. So it's almost like the const, const, const of Java. Okay. Now here's an example of pi, a var. Pi is a variable name, equals 3.14. Okay, and let's say again I run this cell. Okay, it takes a few seconds and then it says 3.14. Okay, and the data type is double. Scala automatically figured out that 3.14 is actually double. Okay, all right. And I have another variable. So this variable pi can be reassigned a value because we defined it as var. Okay, I'm not reassigning it, but you could. Okay, and here's another variable, radius equals 21.5. I run the cell and I get the answer 21.5. It's a double. Okay, then the more complicated 2 pi r. So this is the circumference of a circle, right? I run that and I see the answer is 135.02. Okay, so that's the value of that expression. Okay, all right, so far we just looked at expressions, arithmetic expressions, and also we looked at how to define variables. There are two ways to define it. One is with a val and the other is with a var. Okay, val for constants and var for the regular variables. Okay, now you have to say val or var in front of them. Okay, you cannot just leave it out like in Python. Okay, in Python everything is possible, but here Scala is a very strict typed language, very strictly typed. Okay, almost actually more strictly than Java in some sense. Okay. All right, so we learned very basics of how to introduce variables, and we also saw that there were the two number types, int and double. Of course, Scala, just like Java and many of the other languages, has a whole type hierarchy with lots of types and so on. And I will post the link to the Scala documentation. And if you really get serious with Scala, you will have to learn many more of the built-in data types. Okay. All right, now it's time to learn how to write a function. Okay, remember we are in the topic functional programming, correct? So we have to learn how to write functions. Okay, so this is the first example. All right, here we're defining a function which takes a number and returns a square of the number. Okay, so the function, the first line here is called the header or the signature of the function. Okay. Actually, until this point, until the equal to signature. Okay, very much like in Java too, you have the public static void, whatever. Okay, all right. Here's a function, and now functions are usually almost always defined with the def. Okay, we will come to the subtlety and what's the difference between def and var and val later on. Okay, but functions are usually done with def, very much like in Python too, right? In Python we have def and then the function. All right, after the def, you must have the name of the function. So here it's called square. Okay, and then in parentheses, you have to list all the parameters. Okay, now unlike lambda calculus, you can define multiple parameters. Okay, so in this case, only one, but you can use more than one parameter. Okay, and here the way you define the parameters is name of the variable, then a colon, then the data type. Okay, so that's how the parameters are declared. Okay, little different than in Java. In Java, normally you'll say int x here, right? So here the type comes after the variable, okay, after the colon. Anyway, x colon, you have to get used to this a little bit, okay? Of course, we're going to write some Scala programs over the next 4 weeks or so, but it's not going to be heavy duty like the previous assignments we had, okay? All right, so that's the signature until that point. And then we have to say equal to, and then we have to say the body. Okay, so this is almost like the lambda with a name square. X is the parameter. Okay, and then what is written after the equal to is the body. Okay, body of the function. In this case, it is x times x. Correct? X square. All right. So and that's all there is in the whole function. is defined. Okay, so when I run this cell, this square function gets defined inside the interpreter, and it just says define function square. Okay, now I can start using it. Okay, so here I'm calling it with square 2. Okay, and I get 4. Okay, and the next one I'm doing square of 5 plus 4. Okay, what do you expect? 81, right? 5 plus 4 is 9, and square of 9 is 81. Okay, I can also call the function output of the function as input to the next call. So this will be square of 4. So initially square of 4 will be calculated, which will be 16, and then square of that will be calculated, and you'd get 256. Okay, so this is how you compose functions in functional programming. Okay, and this is a very important aspect of functional programming. You already saw some examples in in the homework 5, lambda calculus, how we composed one apply over another apply, and so on and so forth. Okay, that's exactly what's happening here as well. Okay, all right. So that was the very simplistic function square. Now we have another example, sum of squares. Okay, so this is another function, def sum of squares is the name of the function. Okay, and it's got two parameters, x double and y double. Okay, so there are two parameters, x and y, both of them are double, and equal to designates that's the end of the signature line, and then the equal to is the value, and the value is the body there. Okay, which is, in this case, I'm just calling the previous function. Okay, square of x and square of y, and then adding the two values, square of x plus square of y. Okay, so sum of squares is a function which takes two numbers and then returns x squared plus y squared. Okay, so when I run this cell, okay, it just says that the function has been defined, and then in the next cell I can call this function sum of squares 3 comma 4, and then I get 3 squared plus 4 squared, which is 25. Okay, let's do one more before we get to the next topic. Okay, so here's def power x double y int. Okay, so this is another function called power. X is double. Okay, it's the input. Okay, y is also an input, which is integer, and this is going to compute x to the power y. Okay, and you can see that for a change, I put the return type of this function here. Okay, now technically that's necessary in all the other functions too. Okay, even the sum of squares and then the square and so on. But sometimes you can leave them out if Scala has the ability to figure that out on its own. Okay, I guess even in this case it could be left out, but this just shows you that you may have to give the return type if Scala cannot figure out what the return type is. Okay, anyway, that's where you put the return type. Okay, so it looks almost backwards like in Java. In Java you say int on the front, then you say power, right? Int in the front of, double in the front of power means the return is double. Okay, and then power is the name of the function, and then the parameters, and then you start the brace, right? So it looks like it's sort of backwards. The return type is always at the end. Okay, very much like in the here as well. Okay, x colon double. All right, so here I'm not writing a sophisticated power function. I'm just calling a library function. Just like we have java.math, there's a scala.math package. Okay, and by default in this notebook it gets imported, but otherwise you have to say import scala.math.star above. Okay, in the beginning of a program, very similar to Java. Anyway, so here I'm just called that function POW. That's called power function within the math library of Scala, and I provide the x and the y, and it gives me the correct answer. Okay, x to the power y. Okay, so here the function gets defined, and in the next cell I run program or call that function. Okay, power 2 comma 3 will give me 2 to the power 3, which is 8. Okay. All right, so this is a quick and easy intro to Scala. How to define variables. There are two ways, val and var. How to define simplistic functions. Okay, def, and then the name of the function, and then in parentheses all the parameters, and then colon the output type or the return type. By the way, functions in Scala always must have a return type. Okay, because this is functional programming we are learning. Okay. In Java, you have the return type called void, which you write for functions which are methods which don't have any return values. Correct? There is something similar to that in Scala. It's called unit, but we may not use it very much in this class. Okay. Anyway, so that's and then of course you write an expression as the body of the function. Okay, uh, expressions are just values, arithmetic expressions, Boolean. We'll learn a few other types of expressions soon. Okay, all right. So we have learned the very basics. We learned what the different programming paradigms are, and then the very basics of Scala variables and expressions and how to define some functions. Okay. Now let's get to a little bit of the semantics. Okay, it's important to know this. Okay, before we get to the more of the syntax and more of the features of the Scala language. Okay, uh, there are the main method function. Now we have to worry about how functions are evaluated, right? So this is very much like the lambda calculus, the beta conversion. Okay, it's actually the same as the beta conversion. Okay, exactly same. Okay, so if you understood the beta conversion in lambda calculus, this part should be a breeze. Okay, all right. And the default beta conversion method is called the call by variable. Okay, in programming languages. So the function evaluation, how does a function get evaluated? Okay, and there are two methods to evaluate. There's one called call by value and the other one called call by name. Okay, and we're going to learn call by value strategy first because this is the default. Okay, this is what is available by default in Scala, and it's also the default available in lambda calculus in the beta conversion. Okay. All right. So the general idea behind call by value for a function evaluation is the function may have arguments, right? The actual parameters which you pass. There may be more than one, right? In lambda calculus, it is limited to one, but in general, in Scala, you can have many. So step one is to evaluate all the functions from left to right. All the function arguments left to right, one at a time. Okay, find their values first. Okay. So if there's an expression sitting in one of the arguments, you have to actually find its value. Okay. So once all the arguments values are determined, okay, then what you do is you apply the substitution. Remember in lambda calculus, you had the substitution. You take the body, and then on that body of the function, you apply the substitution. So here, the substitution would be the first formal parameter variable will be replaced by the value which was in the first argument. Okay, and so on. The second variable will be replaced by the second argument value, and so on. Okay, so whatever values were determined after they were calculated left to right on the arguments, those would be used to substitute the variables in the function. Okay, and just like beta reduction. Okay, beta reduction of lambda calculus. Okay, so here's an illustration of what is happening in the execution. Okay, so let's say that we have sum of squares 3 comma 2 plus 2. Okay, so that's the function call. Okay, we have made a call to the function. Remember, the sum of squares just a little earlier was defined as here in the cell number 11. Okay, it was defined as the body was square x plus square y. Okay, you have to remember that. Okay, anyway, coming back to the sum of squares 3 comma 2 plus 2, how will Scala go about evaluating it? Okay, basically, how will it run this? Okay, so as we mentioned before, you have to evaluate each of the arguments independently. Okay, so the first argument is 3. It will be calculated. Okay, 3 is 3, so nothing really happens. The 3 is 3. And then the second argument, 2 plus 2, will be calculated. So 2 plus 2 will become 4. Okay, so now we have the values for all the arguments, 3 and 4. So the sum of squares call will become 3 comma 4. Sum of squares 3 comma 4. Okay. And now what we do is we replace or substitute. Okay. If you go back to the sum of squares, the actual arguments were called x and y. Okay. Or actual parameters. Okay. Not actual. The formal parameters were called x and y. Okay. So now what will happen is that x will be replaced by 3. And y will be replaced by 4, where in the body of the function. Okay, and the body of the function was square x plus square y. Okay, so you can see that the body of the function is written next in this evaluation, and the x has been replaced by 3 because of this value 3 here, and y has been replaced by 4 because of that 4 there. Okay, so now we have square 3 plus square 4. Okay, and then now you repeat the process. Okay, Exactly same process. Okay, so now we are encountered with the square of 3, correct? So that's again a function call, okay, or a function application. Okay, so what do? You go to the definition. No, first not definition, but you first evaluate the values inside this. Okay, but here it's a 3, so 3 will remain as 3. Then what you do is you go to the body of that square function, and if you remember, it was x times x. Okay, so you will replace the body of the function by substituting x by 3. So the x times x will become 3 times 3. Correct? So that's square 3 will become 3 times 3. The square 4 will remain 4 because we haven't reached that point yet. Okay. All the evaluations happen left to right. So 3 times 3 will be calculated and you get 9. Oops, I hit that double click again here. Okay, so let me go back to this cell. So the 3 times 3 became 9. The square 4 remained there. Okay, then the 9 remains here, but the square 4 will be calculated. Again, you will substitute y or x by 4 in x times x, and then you'll get 4 times 4. And the 4 times 4 will be calculated to be 16. And then 9 plus 16 will be 25. Okay, so these are the steps which is taking place underneath when you call the sum of squares 3, 2 plus 2. Okay, and remember the evaluation method is called call by value, and the reason it's called call by value is because the argument values in the call. Okay, these values are calculated first independently. Okay, and then their values are used in the substitutions later on. Okay, got it. It seems this example is pretty simplistic. Okay, but in general, this is the only method available. Okay, so the above strategy is called substitution model. Okay, very much like the lambda calculus. It's formalized from the lambda calculus. And finally, the whole evaluation reduces the expression to a value. Okay, in this case, it was 25. Okay, let's look at a small, tiny example which answers this question. Does every expression evaluate to a value in finite steps? Okay, and the answer is no. And here's a small program. Okay, here's a program. Def loop is the name of the function. Okay, not a program but a function. Loop doesn't take any parameters. Okay, so that's why the left and right parentheses are not there. Okay, that's fine. Okay, that's allowed here. I'm not sure whether it's allowed in Java. Probably not. Okay, anyway, this 0 parameters functions can be written. Okay, colon, and the return type is int equal, and then the body is a call to the same function. Okay, loop. Now this you can easily imagine this is an infinite loop, right? I mean, this function by itself is harmless until you call it. Okay, or once you call it, then it gets stuck in the infinite loop. Okay, because loop there's no call by value because there's no parameters. So you just replace loop by loop. Okay, loop by loop, and then this loop will be replaced by loop and so on, and this will be stuck in the infinite loop. Okay. So the answer to the question is you can have infinite loops even in functional programming. Okay, so all right, we have another 2-3 minutes before I end this video, so I want to, or 4-5 minutes maybe, because I do want to make each video about 30-35 minutes at the most, so there is some time for you to digest it. Okay, so let's quickly do the call by value. Okay, excuse me, call by name, which is the second call mechanism. Okay, call by name. Okay. The idea here is do not reduce the function arguments to values, but delay evaluating until the very end or until necessary. Okay, so that's the key here. Okay, in the call by value, you have to evaluate the arguments, function arguments. Okay, and get a value for them, and then you have to replace. Okay, or substitute. But here you can go ahead and start substituting even without calculating the values. Okay, let's see what happens here on the sum of squares 3, 2 plus 2. The same example. Okay, sum of squares, but now we are applying the call by name strategy. Okay, now by default, if you run this, only call by value will be executed on this. Okay, but if you want this to run using call by value, call by name, we'll learn how to do that later on. Okay, but if you just type this into the interpreter, it's going to use the same method as what we learned before. Okay, call by value, because that's the default. Okay, but call by name mechanism can be invoked sometimes. Okay, and let's see how it'll work if it is called by name. Okay, so 3, 2 plus 2, we will not calculate the values. Okay, we'll just leave them as it is, and then we'll substitute x by 3 and y by 2 plus 2. Okay, so that's why we get square of 3 plus square of 2 plus 2. Okay, remember we delay calculating arguments as much as possible. So this is the lazy evaluation it's called. Okay, So square of 3 plus 3, excuse me, square of 3 will be 3 times 3, and then we carry over the rest of it. Okay, so now we are left with 3 times 3 plus square of 2 plus 2, correct? Now we have to evaluate 3 times 3. There's no choice but you have to evaluate now. Okay, so time has come to evaluate 3 times 3, so it becomes 9. Okay, now we had to go to square of 2 plus 2, right? Now we apply the definition of square of 2 square of x, and we don't calculate 2 plus 2. Okay, why? Because we are in call by name, right? So the body of square was x times x, so x will be replaced by 2 plus 2, so this will become 2 plus 2 times 2 plus 2. All right, then in the next line you'll see the first 2 plus 2 will become 4, and then the next line you'll see the second 2 plus 2 will become 4, and then the 4 times 4 will become 16, and then 9 plus 16 will become 25. Okay, I think if you've already noticed, there is already something you've noticed, and that is that call by name seems to calculate 2 plus 2 twice. Okay, whereas call by value in calculates 2 plus 2 only once. Okay. Understood? Right? You can actually see both the traces, and you'll see that. Okay, so it seems like call by name introduces some kind of inefficiency. But there'll be another example later on. We'll see where the call by name is actually superior. Okay, all right. So, but the basic idea behind the two you need to understand. Okay. Now, in general, call by name and call by value mechanisms both will result in the same value if the following two conditions are satisfied. Okay. The expression consists of pure functions. We are not getting into some of the other non-functional features of Scala. Okay, so if you're talking about pure functions, all the reduced expressions are pure functions, and also both the strategies will terminate. Okay, that is, they don't get stuck in an infinite loop. Okay, so that's so really the answer is the same in both. Like in this case, 25. Okay. But in some situations, the answer may be different. Okay, I mean, not really different in the sense that in one of them you may get the answer, but in the other one you get stuck in an infinite loop. Okay, got it? But call by value evaluates the arguments once, but we already saw call by name can do it twice, right, or more. Okay, and call by name delays the evaluation and can get lucky in not evaluating if argument is not needed. Okay, so we'll see that example in the next couple of slides here. Okay, so let's see whether we can quickly let's see, is it time? Okay, maybe it's time to stop this mini module. Okay, so we're going to stop. We learned call by value and call by name, but we're going to discuss a little bit more of the subtle points behind both these mechanisms in the next lecture. Okay, see you soon.